So good morning students. Well, after that short miley, let us start our class today. Yesterday I had given you an MCQ on the variation of phases of a in velocity resonance. During velocity resonance or with the variation of the frequency, how the phase of the velocity changes. That means we have seen yesterday, so variation of phase difference between velocity and driving force frequency, between velocity and driving force frequency. We have studied this yesterday. We have observed the following. If we go by the diagram, well, you see, this was what we had observed yesterday. What is it? That if this is your phase angle phi, all right, and well, if this is your, suppose say, omega, all right, so what is it that we observe? That this phase angle actually varies from the velocity leads by plus pi by 2 to, you can show that it leads by plus pi by 2 to lags to minus pi by 2 with the variation of omega. Okay, so if this is your frequency omega naught, well, your graph will go like this for phase, for velocity resonance. Okay, so if this is, it should cross through omega naught and then it is like this. So if this is your omega naught, suppose say, all right, so basically what is it that we had observed yesterday? Yesterday we had observed that when the driving frequency is low, at low frequency, that means when omega goes to 0, then phi is equal to minus of pi by 2 here. Okay, all right. So what is it that we are studying? The variation of phase difference between velocity and driving force frequency omega. Okay, so at high frequency, when omega goes to infinity, what happens? Well, you have observed yesterday that phi, so when omega is going to infinity, phi is equal to plus pi by 2. And at resonance, when omega is equal to 0, there is no lead or lag. So at resonance, when omega is equal to omega naught, then what happens? Phi is equal to 0. There is no phase lead or phase lag. So you had an MCQ question yesterday on this. So this is something which you need to understand for velocity resonance and energy resonance, because energy is half mv square. Now what one needs to discuss when you discuss resonance is the sharpness of resonance. The sharpness of resonance. Okay, you need to discuss the sharpness of resonance. Okay, so what is sharpness of resonance? See, the displacement amplitude of a forced oscillator, what is it given by? The displacement amplitude of a force oscillator A is equal to F0 divided by square root of 4k square omega square minus of omega square minus omega 0 square whole square, isn't it? So at resonance, the frequency of the applied force, what will it be equal to at resonance? What happens at resonance? at resonance, the frequency of the applied force should be equal to the frequency of the oscillator. So omega will be equal to omega naught, or omega square minus omega 0 square whole square, or this is equal to 0. Okay, alright. So the amplitude of the forced oscillator during resonance. What do we observe regarding the amplitude of a forced oscillator during resonance? We have seen that the amplitude A, we have already observed this. If you just listen to the video, you will see it is equal to F0 by 2k omega, isn't it? What is F0? F0 is the applied force per unit area, per unit mass. F0 is equal to F0 by m, isn't it? The applied force per unit mass, and omega by 2 pi is the frequency of the applied force, okay, and k is the damping coefficient. Alright, so frequency of the applied force is omega by 2 pi and k is the damping coefficient. Okay, now as the frequency of the applied force omega is increased or decreased, so if you keep on increasing or decreasing the frequency of the applied force from the resonant value omega naught, the value of the amplitude will always decrease. Okay, so whether you increase omega or decrease omega, the value of the applied force, isn't it, the value of the amplitude, sorry, that we have been plotting for amplitude resonance will always fall down, isn't it, as you increase or decrease this factor. Now when the amplitude at resonance rapidly falls with slight change in the frequency of omega, or with slight change from the resonant value, rapid decrease of amplitude with small change of omega, with small change of omega. You call the resonance to be sharp, is the sharpness of resonance. As you understand from the definition itself, if it changes, is the sharpness of resonance. Okay, alright. So when the amplitude at resonance falls rapidly as the frequency omega of the applied force is changed slightly from its resonant value, the resonance is said to be very sharp. Okay, so when the amplitude at resonance falls gradually as the frequency omega of the applied force is changed slightly from its resonant value, then the amplitude is said to be flat. Otherwise, for gradual change, we call the resonance to be flat. We define the resonance as flat. Okay, alright. So how do you picturize, how do you show it in your diagram, the sharpness of resonance? Let's see. Okay, let us observe how one shows the sharpness of, picturizes the sharpness of resonance. Okay, so let us draw the diagram for sharpness of resonance. Okay, so if this is your amplitude, okay, this we have already drawn, but anyway we can do it once more. Well, you can show that All right, so this is becoming flatter. All right, so this is happening at omega equal to omega naught. This is omega. So it becomes sharper and sharper as your damping constant increases. Okay, you can make it still sharp like this. It will go still high and it will be still very, very sharp. So this is how we consider the sharpness of resonance. So what is the effect of damping? As you know, this is maximum damped. So R1, R2, R3, R4, R1 greater than R2, greater than R3, greater than R4. Okay, so what are the conditions for what is the effect of damping on the sharpness of resonance? See, when K is equal to 0, that means when there is no damping, the amplitude of resonance becomes infinite, isn't it? Okay, when the damping is small, when K is small, okay, the amplitude is sufficiently large but falls off rapidly. It is large but falls rapidly, isn't it? Falls rapidly. All right, now as the value of K increases, when K increases, what happens to the amplitude? The amplitude at resonance decreases, but the curves fall off gradually. So amplitude falls gradually. All right, and even when the frequency of the applied force is a little different from the natural frequency of the body, the amplitude is nearly the same. You will see. In other words, when damping is small, resonance is sharp. When damping is large, resonance is flat. Okay, so this is quite important. When damping is small, resonance is sharp. Resonance is sharp, and when damping is large, resonance is flat. Okay, when damping is large, resonance is flat. So let's stop over here today. All right, for this video. This is all that you have to do for your forced vibration. All right, now I'll be doing problems. I'll be doing some problems with you all, and I'll be asking you to do some problems on pre-vibration, damped vibration and forced vibration. Okay, so that will be my last video for today, and the rest you will be doing. All right.